Hello there, and welcome to my video on voltage dividers. So before we get into this, you might ask yourself, why voltage dividers? What's the big deal? Well, voltage dividers, I have found, are key to really understanding transistor theory. I don't know about you, but it wasn't enough for me. Yeah, I could just memorize some basic rules about transistors, common base, common emitter, and how this goes and what that goes. But I really wanted to understand them. And a long time ago, when I was studying transistors, I figured out they are really just a big automatic voltage divider. In fact, have you ever wondered where the name transistor came from? It stands, or shorthand, for transfer resistance. So, if we're going to transfer resistance, we have to learn a little something about resistance, and actually, there's some magic that goes on with voltage dividers. They're pretty simple, but when we understand them, and I'm going to show you something that you may never have thought of, this may help it all make sense. So let's look at this voltage divider, 12 volt source to ground, R1, R2, and R3. R1 is 6 ohms, R2 is 4, R3 is 2 ohms. So if I wanted to know my voltage at A, B, and C, so my total resistance, of course, is 6 plus 4 plus 2, or 12 ohms. So my total current using Ohm's law is 12 over 12, or 1 amp. If I want to know the voltage at A, well, the voltage at A is 12 volts. The voltage at B, I take by adding the resistance of R2 and R3, which is 4 plus 2, and then I divide that, or multiply that, by 1 amp. So that is 6 volts. And then the voltage at C will be 2 volts. Pretty basic Ohm's law application. But let's look at this a little further. Suppose it was a little more complex. Suppose R1 is 470 ohms, R2 is 47 mega ohms, and R3 is 130 ohms. In that case, our resistance total will equal 47,600,000 ohms. And our current, if you do the calculation, is 2.55 times 10 to the negative 7th amps, or we can do this, 1, 2, 3, 4, 5, 6, 2, 5, 5, because I got a negative 7. 1, 2, 3, 4, 5, 6, 7. So it's that many amps. It's 0.255 microamps. That's my total current. In that case, my voltage at A is still 12 volts. My voltage at B is 47 meg plus 130. Times this number, and that equals to 11.985 volts. And then C is kind of unimportant. B here, with this high resistance, just keep this in the back of your mind, and we'll talk about this more in another video, is the same as a transistor turned off. So you'll notice that here's 12 volts, there's 11.985, and there's a very slight amount of current still does flow through this circuit. But nearly line voltage is felt at B with this high resistance. So let's decrease our resistance by an order of 1,000. Now here, my total resistance is 40, total resistance here, right, is 4,700 plus 600 equals 5,300 ohms. 4,700, 4.7K plus 600 is 5,300 ohms. Now look what happened. Look what's happened to my current. I have 0.0023 amps flowing, and my voltage here at B equals 4.7K plus 130 ohms times 0.0023 amps, which equals 11.109. So I have 11.109 here, and here I still have 12 volts. So you'll see that now all of a sudden my voltage here, as this resistance has decreased, this voltage has decreased also, and then of course correspondingly you know C is going to go up. That's not really too important, but remember now this is like a transistor starting to turn on. Right, and I've got a little more current flowing up through here. My voltage has decreased at B as the resistance of R2 has decreased. Let's take it down further. Let's go down another order of 100. Here, my resistance total is 470 plus 47 plus 130, or 647 ohms. Now, all of a sudden, my current has jumped up to 0.019 amps, or 19 milliamps. That's quite an increase in current. Doesn't seem like a lot, but we've gone from 0.255 microamps to 19 milliamps. Quite an increase, significantly greater increase in current. My voltage at A is still 12 volts, and now my voltage at B has gone down to E sub B equals 3.36 volts. How did I get that? 130 plus 47, these two resistors, times 0.019 amps. And that equals 3.36 volts. So now that is like this transistor fully conducting. And notice the voltage here at B has decreased greatly. Kind of look at this graphically a little bit. Here's this same voltage divider, and R2 is shown as a variable resistor. And where R1 is still 470 ohms, R3 is still 130, and R2 varies between 47 ohms and 47 mega ohms. Just a little graph here. As R2's resistance decreases, as you can see that going down, then the voltage at B increases over time. Keep this in mind, and the next video we'll talk about how this applies actually with transistors and the magic of how transistors work, the transfer of resistance. Thanks for tuning in. See you on the next video.